Everyone. My name is Shaminda Bandara and I am a PhD student at Johns Hopkins University. Today, I am glad to present our work on hyperspectral pan-sharpening. We propose a textural and spectral feature fusion transformer for pan-sharpening called HyperTransformer. Hyperspectral pan-sharpening aims to spatially enhance low-resolution hyperspectral images by transferring textural details from high-resolution panachromatic images while preserving the spectral characteristics of original low-resolution HSIs. The early research on hyperspectral pan-sharpening employed component substitution, multi-resolution analysis, Bayesian, and variational methods. Recently, deep convolutional neural networks have also been introduced for pan-sharpening. However, state-of-the-art approaches often adopt straightforward ways to transfer spatial details from pan image to low-resolution HSI. In contrast to these conventional pan-sharpening approaches, our hypertransformer utilizes an attention mechanism to extract cross-feature space dependency between pan and low-resolution HSI features and finds texturally advanced and more spectrally similar feature representations for low-resolution HSI before fusion, which greatly helps to obtain pan-sharpened HSI with simultaneous high spectral and spatial qualities. Our hypertransformer consists of three interconnected modules, namely two feature extraction modules for pan and low-resolution HSI, the attention mechanism, and the textural spectral feature fusion module. We first transform pan and low-resolution HSI images into their feature space by employing two feature extractors. We then utilizes low-resolution HSI, pan down up, and pan features as queries, keys, and values in an attention mechanism to compute texturally advanced and spectrally similar feature representations for low-resolution HSI features. The computer's texturally advanced feature maps are then mixed with low-resolution features from a backbone network which constitutes the pan-sharpened HSI. Here we present our final pan-sharpening network. Unlike the conventional pan-sharpening methods that use textural features from pan only at high resolution scale, we index textural details from our hypertransformer to the backbone at multiple spatial scales. Furthermore, to obtain visually appealing pan-sharpened HSIs, we also introduce two new loss terms to the hyperspectral pan-sharpening, namely the perceptual loss and transfer perceptual loss. Let us now compare the pan-sharpening performance of our hypertransformer with existing state-of-the-art methods. We use three publicly available and widely used HSI datasets for our experiments. We compare our model with both classical and convex-based state-of-the-art methods. As shown in the table, our hypertransformer significantly outperforms both classical and convex-based state-of-the-art methods on all the three datasets. This figure shows visual evaluation results from the testing set of each dataset. We present the synthesized RGB images along with the corresponding mean absolute error maps between the reconstructed HSI and the reference HSI. As can be seen from the MAE images, our hypertransformer achieves significantly lower MAE than all the other methods. Let us now move on to the ablation studies. In this ablation study, we demonstrate the effectiveness of the proposed hypertransformer on hyperspectral pan-sharpening. We consider the baseline as the pan-sharpening network without the feature attention mechanism. From the MAE plots, we can clearly see that the reduction in MAE over the spectral bands when we utilize our hypertransformer. In this experiment, we present the results when we increase the number of global descriptors in our hypertransformer from 1 to 64. We can see that the increasing the number of global descriptors results in significant improvement over the spatial and spectral performance measures. However, after n equals 16, the performance metrics start getting saturated. Therefore, we set n equals 16 as the optimal value. In this ablation study, we show the effect of injecting textural features at multiple spatial scales. From the table, we can see that the best pan-sharpening performance is observed when we utilize our hypertransformer across all the three spatial scales. This table shows how each loss function improves the quality of hyperspectral pan-sharpening. Combining the synthesized perceptual loss with L1 loss improves the pan-sharpening performance. It is further improved by transferred perceptual loss. In conclusion, we propose a novel textural spectral feature fusion transformer for pan-sharpening. The experiment conducted on 3 HSI datasets demonstrated the superiority of our method over the state-of-the-art methods, making it as the new SOTA for HS pan-sharpening. Thank you. Hello